Our first topic, complex numbers. And I guess the first bit of news is, well, you've been dealing with complex numbers all your life. We'll soon see why. Now, the actual idea of complex numbers started with the problem of solving a cubic. But it's more commonly associated with solving quadratics. So let's have a look at solving quadratics. I get something like this: x squared plus 1 is equal to 0. And we go, oh, x squared equals negative 1. Oh, you can't do that. No solutions. But it's the same problem that we've had all through maths when you think about it. When back in primary school, we would have said, oh, what's 10 minus 20? And you would have gone, can't do it. 20 is bigger than 10. Because we didn't know about negative numbers. And even before that, you would have said, oh, what's 3 divided by 4? And you would have gone, 4 don't go into 3. Can't do that. And then you learn about fractions. So every time these problems come along, we create a new set of numbers, which allows us then to continue with the maths and solve more problems. So that brings us to this one, where at this stage we're saying, oh, can't do it. No solutions. But notice I haven't put no solutions, I put no real solutions. So we define now a new number, which allows us to solve the problem. And that new number is in fact a letter, and that letter is I. And it's defined to be the square root of negative 1. Now, what is the square root of negative 1? Don't know. But that doesn't stop us in exactly the same way as we don't know the square root of 2 either. But we're happy to use the square root of 2 in calculations. So there is no difference, really. More formally, the definition is actually I squared is negative 1. I mean, yeah, okay, same thing, but I squared is negative 1. I is an imaginary number, and I guess that's where they got the letter I from. Although you do sometimes see them use J. Not that common, but you do sometimes see J used for it. So let's go and solve the problem. X squared equals negative 1. We can now say, oh, well, that means x equals plus or minus, of course, in the same way as if we had x squared equals 4, we would have said the answer was plus or minus 2. So we're saying, well, it's plus or minus the square root of negative 1. Ah, but we know what the square root of negative 1 is. It's I. So plus or minus I would be our answer. So that's the basic idea, which will now allow us to do more problems. Every complex number can be written in this form: x plus iy. What are these bits? We have a real and imaginary part. The real part is the bit without the I. So x, that will be a real number. So that's the real part. The imaginary part is the bit with the I. Now, y is still a real number. It's a bit like what we saw in vectors. It's like the scalar times. So y is times that imaginary part. So if they ask for what's the imaginary part, you don't put the I down. You just say, well, what's the coefficient of I? That's the imaginary part. Let's do a very quick example then. So you have 3 plus 5i. We'd say, oh, well, the real part of that is 3. The imaginary part is 5, not 5i, but 5. Now, if the real part turns out to be 0, then z is an imaginary number. It has no real part. So it's purely imaginary. Examples of that: root 3i minus 6i. Well, any multiple of I guess, would be one. Now, if the imaginary part is equal to 0, then you have a real number. And that's what you've been dealing with your whole lives. These set of complex numbers where the imaginary part happened to be 0. So you have been working with complex numbers. Here's an example of real numbers: 3/4, pi, e, -4. They're all real numbers. Now, every complex number has a conjugate, just like we saw in surds, because if you think about it, these numbers are actually surds, because I is the square root of -1. So just like surds have conjugates, we have conjugates here in complex numbers as well. So x plus iy, its conjugate would be x minus iy. And notice the notation, you see a bar above the number, then it's saying the conjugate of this. -2 minus root 7i, then its conjugate will be -2 plus root 7i. So unlike when we're dealing with surds, where it didn't matter which one you changed the sign on, here it must be the imaginary part you change the sign on. Okay, so let's now look at our set of numbers. Real numbers is what you've been dealing with so far. And we know they're real because we can place them on the number line. Or probably more accurate to now say the real number line. Symbolised with the hollow R Inside there is a subset, the rational numbers, which we symbolise with Q. Q, of course, standing for quotient. And then we have the irrational numbers. Well, they're all the numbers that aren't rational. And there's not actually a symbol for irrational numbers. If you wanted to, you could say R\Q, which is simply saying the real numbers, but not including all the rational numbers. Very rare to use that notation, but if you wanted to, I suppose that would be what you'd use. Okay, inside the rational numbers then, we have fractions, and by fractions, I mean not the ones that can be simplified down to be whole numbers, because then we have the whole numbers, or the better word mathematically, of course, is integers, symbolised with Z, because that comes from the German word for integer, Zahlen. Inside the integers, we have the natural numbers, symbolised with N. Then, of course, we have a lovely little set all by itself, 0. And 0 is that really weird number. Some people even say it's not actually a number, because 0 is nothing, so how can it be a number? You know, and strange things happen with 0. Like you can't divide by 0, for example. Now, overlying all those, we have the negative numbers. So you can have negative fractions, you can have negative integers, you can have negative irrational numbers. You don't really have negative 0, so it doesn't overlap there. You don't have negative natural numbers, because natural numbers, I guess another name for that are the counting numbers, and you usually start at 1, 2, 3, and so on. Okay, so that's what we've been playing with so far. But what I'm saying to you is they actually belong in this bigger set of numbers, the complex numbers. So now over on the other side, we have the imaginary numbers. Now, the imaginary numbers are x equals 0. So there are some that belong outside those two boxes. They're just complex numbers. By imaginary numbers, I'm talking about the purely imaginary numbers. But the thing about imaginary numbers is you cannot order them. See, unlike the real numbers, we can say, well, 5 is bigger than 4. But we don't say that with imaginary numbers. It's not true to say 5i is bigger than 4i. And it's certainly not true when you talk about complex numbers where there's a part to both. Which is bigger? 1 plus 2i or 2 plus 1i? Which one's bigger? It doesn't make sense. So we can't order these new type of numbers. How do we play with them then? Basic operations, well, I is a surd. So all our rules for surds apply here. So if I want to add, you could also think of it like algebra, because you think, oh, well, I is a pronumeral. We just add like terms. So yeah, okay, minus 4 minus I. Subtract, same deal again, just like algebra. 12 minus 5i. Multiplication, binomial product. First outside, inside last. But what we now have to be careful with is this I squared. Because whilst we don't know what I is, we do know what I squared is. Because it's defined to be -1. So we never leave it as I squared. That would become plus 6. Most of the time you wouldn't even write the minus 6i squared down. You just write plus 6 straight away, because you've done the calculation. But of course, negative 32 and 6 add together, giving us negative 26 plus 32i. Division's a little bit different. It's what we call realising the denominator. Because what you're really doing is rationalising the denominator. 4 minus 3i divided by minus 8 plus 2i. Well, realising the denominator is actually rationalising the denominator. We multiply by the conjugate. Same deal. So I'll multiply by minus 8 minus 2i on minus 8 minus 2i. So the top of the fraction, there's the binomial product that we do. The bottom of the fraction becomes the difference of the two squares, but in this case it's now going to be the sum of two squares because of the I squared. Be careful with that. It's such an easy mistake to make, is to go minus 4 here instead of plus 4, because we're so used to rationalising the denominator and getting a difference of two squares. So the bottom is actually the sum of two squares, 64 plus 4. And on the top, what do we get? Minus 38 plus 16. I've broken that into the two parts. And if they were to say, write it in the form x plus iy or something like that, they're saying to you, yeah, I want you to write it in two parts. So you wouldn't leave it as a single fraction. You would actually break it up and say, oh, this is the real part, this is the imaginary part. So minus 19 on 34 plus 8 on 34i. So these conjugates, just some basic ideas about conjugates. It does not matter. If you want to find the conjugate of two numbers added together, you can either add them together, then find the conjugate, or find the conjugate of each individual one, then add those. It doesn't matter. It'll give you the same answer. Same with multiplication. The order doesn't matter whether you do the conjugate first or take the conjugate last. Same with division. Z times Z conjugate becomes interesting. Remember, that's the bottom of the fraction we just saw, becomes the sum of two squares. Not just any two squares though, look at it. X squared plus Y squared. We've seen that somewhere. In vectors we saw it, and it was, well, almost the magnitude. It was the magnitude squared. So that will become a very useful idea. If I want to find the reciprocal of a complex number, the quick way of doing it is simply go, oh, it's conjugate over Z conjugate, sum of two squares. Because think about it, what would you do if you could actually do the reciprocal? You would multiply top and bottom by the conjugate. Well, the top's 1. So you end up with the conjugate on top, on the bottom you get the sum of two squares. So it's very quick to find the reciprocal of a complex number. Let's do this one then. 1 on 4 minus 3i there, I would say, oh well, conjugate goes on top, sum of two squares on the bottom, and we end up with 4/25 plus 3/25 I. Now why do that? Why do we realise the denominator? And again, it's about comparison with other numbers. I can now break that into the real and imaginary part. When it was written as a fraction, 1 over 4 minus 3i, I don't know what the real part is and the imaginary part is, because that's not how fractions work. I can't say the real part is a quarter and the imaginary part is 1 on minus 3i. You don't split the denominator like that. You split the numerator like that, but not the denominator. So that's why we need to get the imaginary into the top. So equations then. How do we solve equations now that we have these new numbers? Real and imaginaries can never meet, if you like. Because a real thing is real and an imaginary thing is imaginary. So it's a bit, again, like surds, where the real part must equal the real part, the imaginary part must equal the imaginary part. So yeah, A1 equals A2, B1 equals B2. So if I had to solve this equation, there's a couple of ways I could do it. I could expand the left-hand side out and then equate real and imaginary. I could divide both sides by 2 plus 3i and then work out what the right-hand side is. Whichever way. Which way did I go? I've expanded the left-hand side out to just to have a bit more fun. And grouping the real and imaginary, well, that means that 2x minus 3y, that's the real part, that must equal 4. And 2y and 3x, that must equal negative 2. That's the real part. We've basically got simultaneous equations to solve. I'll make the y's the same, so eliminate the y's. I get x is 2 13s, sub back in, y is 16 on 3. Notice the question is not saying what is this complex number, it's simply saying what's x and what's y. So I just leave it like that. X is 2 on 13, y is 16 on 13. You could have simultaneous equations that involve complex numbers. Well, the rules don't change. If I want to solve a simultaneous equation, the idea is make the coefficient of one of the things the same, so we can eliminate them. I've made the coefficient of w the same, so I've multiplied the second equation by 2. I do a subtraction, and I can see, well, z is 2/3 plus 5/3 I. Sub back in, and we can work out w. So exactly the same as we've been doing all along with simultaneous equations, just with this new class of numbers. So my solution, there we go, w is 2/3 minus 5/3 I, z is 2/3 plus 5/3 I.